Welcome back. We're diving deep into a technique that's likely crossed your path if you're navigating the world of red teaming or advanced threat analysis.
Oh, definitely.
Especially for you pen testers and InfoSec pros out there, understanding how adversaries, well, disappear.
Yeah.
It's absolutely critical.
It really is. And today, we're unpacking memory bombing.
Memory bombing.
Think of it as like leveraging Windows' own memory architecture against the security tools themselves.
Okay.
It's kind of the digital equivalent of trying to hide a needle in a haystack, except you build the haystack yourself out of terabytes of allocated memory, basically.
Hoping the security scanner just gets overwhelmed or bored before it finds your actual needle.
Exactly. That analogy pretty much nails it. And the sources we looked at, they lay out the nuts and bolts, how it pulls off that stealth.
And crucially, how you might spot it.
Right. The core idea is overwhelming those dynamic security engines. It's interesting, these techniques really gained traction because signature-based detection got so good,
Makes sense. Attackers were forced into memory, into these fileless methods.
Precisely. So the attacker allocates just an excessive amount of memory,
Right.
usually inside a legitimate process.
Okay, and how do they do that? Just ask nicely.
Well, they use standard functions, things like calloc or malloc.
The standard C library functions for getting memory.
Yep. Malloc gives you raw space. Calloc zeroes it out first. Little difference, but sometimes important.
Mm-hmm.
They use these to carve out just massive blocks.
And this happens in the heap mostly, not the stack?
Yeah, typically the heap. It's flexible, designed for these big dynamic allocations. Perfect for this kind of abuse.
So you get this huge block allocated. Then what?
Then you inject your shellcode into it.
Yeah.
And because the process now has this ridiculously large memory
The
footprint,
security tools just choke.
or they might just give up, or maybe sample tiny portions, completely missing the malicious code hiding in that vast space.
So it's fileless right from the get-go. No disk signatures, which is always a pain point for defenders. You're saying EDR, AV tools.
Yeah.
They can be blinded by just sheer volume.
That's the basic exploit,
Yeah.
Create this unexpected massive memory landscape and your payload gets a free pass to just sit there, waiting. It's clever. Abusing a normal system function.
Okay, that makes sense. Now, you mentioned this isn't always a solo hack. It plays well with others.
Absolutely. Yeah, often paired with other techniques. Two common ones are heap spraying and ROP, return-oriented programming.
Heap spraying. That sounds messy. Is it like spraying the same code everywhere?
Kinda. Yeah, you allocate multiple smaller blocks within that big memory bombing allocation.
Inside the bomb.
Right. And you put the same shellcode or parts of it in each of those smaller blocks. It just massively increases the odds that if you later manage to redirect execution somewhere into that general area.
You land on your code. Predictable placement through redundancy.
Exactly.
Reliability.
Got it. And ROP. That's the classic for bypassing DEP, right? Data execution prevention. Correct. ROP doesn't execute injected code directly because DEP would often block that in non-executable memory like the heap. Instead, you find existing code snippets,
Yeah.
little bits of functions already in memory.
Gadgets.
Gadgets, yeah, from legitimate libraries or the program itself. You chain calls to these gadgets together to perform actions.
Like changing memory permissions.
Precisely. Or calling APIs.
Yeah.
Eventually leading execution maybe back to your shellcode, potentially in that heap space you prepared. Combining memory bombing's evasion with ROP's execution is, well, potent.
So you bomb the memory, maybe spray the code for good measure, then use ROP gadgets to pivot, maybe change permissions on the fly, and then jump to the shellcode. Nasty stuff.
It can be very effective.
So, how do we even start to spot this? Signatures are clearly out.
Right, that's the million-dollar question for defense. You need memory analysis. No way around it. Tools like volatility mentioned in the sources, they're indispensable here.
Analyzing a memory dump, looking for the weird stuff.
Exactly. Looking for anomalies, things that shouldn't be there.
Okay, let's get practical. What exactly are you hunting for with, say, volatility?
Well, first, just abnormal process behavior. Use something like windows.pslist. PSList, maybe, is a process using way more memory than usual. Does it have weird parent-child relationships?
Like, notepad.exe suddenly eating gigabytes of RAM and spawning cmd.exe.
Exactly that kind of thing. That's your first clue. Then, the crucial bit, finding the injected code itself. Plugins like windows.malfind, malfind.
Malfind. Makes sense.
Yeah, it specifically looks for code in memory regions that have suspicious execute permissions.
And what flags a region as suspicious?
You're looking for permissions like page execute or add write. That's a huge red flag, especially for heap or stack memory, which should normally be executable and writable.
Okay. Execute plus write equals bad, usually.
Usually. And within those suspect regions, you hunt for hallmarks of executable code, like the magic bytes 4D5A.
The MZ header, start of a PE file. Even if it's just shellcode, it might have that stub.
Often does. Or other patterns. You can also check network connections with something like Windows.net scan. NetScan to see if that suspicious process is calling home.
Right, connect the dots. That's the forensic gold standard for memory artifacts. Okay, detection is hard but possible. What about prevention? We mentioned DEP.
Right, DEP helps. There's also ASLR address space layout randomization.
Randomizing memory locations makes guessing addresses harder for ROP and Spring.
Exactly. Then there's NX no execute, which is basically the hardware version of DEP. And some systems have heap integrity checks, trying to detect corruption or weird allocations in the heap itself.
So layers of defense. But, as always, attackers find ways. Relying only on these static things isn't enough, is it?
No, it's a constant arms race. What's fascinating really is how attackers take something so basic, so fundamental, just allocating memory,
Yeah, totally innocuous.
and they weaponize it to create these blind spots in really sophisticated security tools.
Okay, so let's recap. We've seen how memory bombing uses just excessive memory allocation, often via calloc or malloc, into the heap to basically overwhelm or evade dynamic security scans. Prime example of fileless execution. We saw how it pairs nicely with heap spraying for more reliable shellcode placement and ROP to bypass DEP.
Right, chaining gadgets.
And defensively, memory analysis is key. Tools like volatility let you hunt for weird process behavior, look for that injected code using malfind, check for those dangerous pages executor add write permissions, and spot indicators like the 4D5A magic bytes.
Crucial steps.
And while mitigations like ASLR, DEP, NX, heap integrity checks help, they aren't foolproof. Constant vigilance, behavioral analysis seem necessary.
Absolutely. Detection can't be the only strategy.
All right, here's a final thought for you to chew on. If attackers can turn simple memory allocation into such a powerful evasion technique, what other seemingly benign low-level system operations could be next? What other everyday functions could be twisted to create the next generation of security blind spots?
That's the question, isn't it? The cat and mouse game definitely continues.